Okay, and so as we were talking about on the other one, there was that this is millimeters here, but it ends up 635 nanometers here when you divided it by these different values right here. So the longest wavelength that can be used is lambda equals 635 nanometers. Now, on to the next section. Here we're talking about gratings, dispersion, resolving problems, power. This has a lot of applications because each of the fine rulings here is 0.5 microns wide on a compact disc. And it serves functions as a diffraction grating. So because what you're doing is you're illuminating a light on that. And so you have colored lanes that are composite of the diffraction patterns from the ruling. And it determines how many of them they can put on there. And if you ever look at an old vinyl phonograph record versus what you have now, you'll see just how fine those are, and in terms of the way in which things can be recorded on there. So the dispersion D of a diffraction grating. Now, so here's D with a completely different measure, right? This is dispersion. This is not distance. I know they just seem to love to try to confuse you. So the dispersion of a diffraction gradient is a measure of the angular separation of the lines it produces for two wavelengths differing by a chain delta L. For order number m at angle theta, the dispersion is given by d equals this angular separation divided by the change in the wavelengths, or m d over cosine theta. Okay, so in this chapter, you're seeing several different equations that are looking similar. And so you're going to have to be very, very certain on identifying what each of the letters stands for in that equation. So thus, to achieve a higher dispersion, we must use a gradient with of smaller grading distance d and work in a higher order m. Note that the dispersion does not depend upon the number of rulings in the grating. The SI unit for D is the degree per meter or the radian per meter, okay? Degree per meter or the radian per meter, okay? So, the resolving power, R, of a diffraction grating is a measure of its reliability, of its ability to make the emission lines of two close wavelengths distinguishable. For two wavelengths different by delta L, with an average right here, the resolving power is given by this right here. So this is R equals L average over delta L equals NM. Grating number does appear in here, okay? So you can see that you have different numbers here. You have different separations here, different angles here, and you can see what their effect is on the dispersion. This is the dispersion number, degrees per micron. And this gives you your different resolving power, okay? So here you've got, for grading A, you have pretty decent separation. Here you've got even better separation here. The resolving power is much greater because these are narrower. These are broader, right? It is not. It's as probably as it is. It's numerically as good as this one, but not as sharp as this one. So practical exercise number 10. And this is problem number 55. Here lambda, you have deuterium and hydrogen emitting red wavelengths at two wavelengths, and this is your mean value. So this is your L average, lambda average. Separation is 0.180 nanometers, right? Find the minimum number of lines needed in a diffraction grating that can resolve these lines in the first order. So we're going to go back to that equation, R, lambda average over delta M, delta lambda, to give you your diffraction grating number. That's what you're going to end up trying to find out for M, right? Okay, so lambda average over delta L means N equals lambda average over M delta L. M here we want to have for 1, right? This is your average wavelength of the two, 6.5, 6.3. Your difference between them is 0.18 nanometers. Okay, that's their separation. And so you need 3.646 times 10 to the third rulings, right? 3,646 rulings in order to be able to separate those two. The final section in this chapter is X-ray diffraction. This is a technique that inorganic chemists have used a lot, and some biochemists have used a lot in order to resolve protein crystal structures. And essentially what you have here is you've got X-rays with electromagnetic radiation. So the wavelengths here are of the order of about 1 angstrom, 10 to the minus 10th meters, okay? So the figure at the right shows the X-rays are produced when electrons escaping from a heated filament, F, are accelerated for a potential difference V and strike a metal target, T. And what you do is you have on that metal target some type of crystal structure. It can be sodium chloride atoms, sodium chlorines, and a lot of times that was how crystal patterns were determined by chemists, for all of the physical chemists, by the way, on all the different ones that are known. And here what you have is different, here's the crystal lattice pattern, and what you're doing here is you have the incident X-rays on there, and it shows how the different ones are diffracting from those surfaces, giving a specific pattern that then determines the distance between different planes on here. So you can get the distance between the different atoms in that type of crystal structure. And when you have sodium and chloride, which have very different molecular or atomic diameters as ions, you can determine exactly how all of those things work out. But it's quite a lot of interesting work that goes into the resolving of a crystal structure. So as shown in this figure right here, if the X-rays are diffracted towards a crystal structure, they undergo what is called Bragg scattering. It's easiest to visualize if the crystal atoms are considered to be in parallel planes. Doesn't always happen that way. You can have ones that are in the center here and all sorts of different packing mechanisms. But for the purpose of the math here, we'll just have 2d sine theta equals m lambda. Again, same form. We just have to determine what the d's are in the different ones, right? So what you're looking at here is the d sine theta. You are talking about the distance between the different packing here, okay? Different layers of the plane. For example, this is exercise number 11, which is problem number 65. Here, an X-ray of wavelength A undergoes first order reflection, which is first order reflection means Bragg law diffraction, means that equation applies, from a crystal when its angle of incidence from the crystal is 23 degrees, and an X-ray beam of 97 picometers, right? Pico. So this is, it undergoes third order reflection when its angle of incidence at that phase is 60 degrees. Assuming that the two beams reflect from the same family of reflecting planes, find the interplanar spacing, that's going to be the d difference between those two, and the wavelength of your X-ray. Okay, first for the beam 2d sine theta 1 equals lambda a, right? For the second one, it's 2d sine theta 2, 3 lambda b. And the values of d and lambda can be determined first getting the d right here. D is 3 lambda 2 sine theta 2. So it's 97 picometers times 2 sine 60 degrees. So your D then, your spacing, is going to be 1.7 times 10 squared picometers. And your lambda alpha, lambda sub A here, is 2d sine theta 1, right? So it's 2 times this distance, okay? Sine 23 degrees, where it comes out the second time. And so you get your lambda, your wavelength, 1.3 times 10 squared picometers, right? So that shows you how you can utilize the values and getting what you have here, right? So anyway, I hope that has been instructive. Here's a summary in the last two slides about diffraction, single slit diffraction and the equations there. Circular aperture diffraction, where you have this factor involved there as well. Rayleigh's criterion, theta sub r equals 1.22 lambdas over d. And this is for the two objects on the verge of resolvability. Okay, what's the angle that they have to be? Double slit, this is the intensity involved. So for double slit, you have this second factor involved there as well. Diffraction gratings, where now you have the slits, all of the different ones that are involved in this equation. So that becomes a part of the equation here. And then for diffraction ones, where here what you're doing is you're using the Bragg's law, which is a variation on one of the other ones, where D right here represents the different planes in that crystal structure. So very similar looking equations, but very different types of applications for all of them. And the lab on Thursday will essentially be one where we talk about interference and diffraction. And by the way, that will be the last lab of this year. So we are winding down. Just one set of series of one more chapter to cover next week. And then the week after that will be when the final exam will be. So anyway, just make certain you understand the distinctions between the different ones. Your homework problems, in case you didn't note earlier, are problems number 5, 13, 20, 36, 45, 56, and 69, as well as answering the questions at the end of this, following this particular slide. Okay, so there's 15 questions there, and then the problems are 5, 13, 20, 36, 45, 56, and 69. And that should do it for you. Any questions, please don't hesitate to send me an email, and I'll be happy to respond.